condition. Okay, so like what I told you before, if we go back to our boundary condition, right, we state this. Okay, we state this, that I'm going to highlight them in yellow now. That when x is equal to 6, we're going to have maximum what? Shearing force, and we're going to have the maximum bending moment. Okay, so likewise, when you see over here, when you see this graph, you see that this at x is equal to 6, right? This point over here is minus 72,000 Newton, and this over here is minus 180,000 Newton meter. Okay, now let's try solving this, okay, without using the integration method, which is also possible. Okay, which is also possible, but there are more steps involved. Okay, but there are more steps involved. So I'm going to quickly, because I think by now, from what I can gather from how you fare in your term test, you are very sure about the positive shear and positive bending moment technique already. Okay, so now let's try using this technique. Okay, so let's try. I'm going to write on the same page. Okay, we're going to draw the same page. Okay, and we're going to start from here. Okay, so we're going to do the same thing, right? I'm just going to show you if we use positive shear and positive bending moment method. Okay, what must you go through? Okay, I'm going to. So we're going to do use the positive shear, right? We're going to use the positive shear. And positive bending moment approach. Okay, we're going to use that approach, and you'll see the difference. So now the thing is this. Okay, so we don't know where so remember, this is a gradient distributed load. So if I were to draw a structure, right, we'll draw our structure. So we started with 6,000. We ended up in 18,000, right? So we have a cantilever beam, right? So point A to point B, right? So if we have a cantilever beam, right? So now the problem is this. So if you now we are going to construct our free body diagram, right? We're going to construct our free body diagram, right? So this is your free body diagram. Okay, this is your free body diagram. So you know how to get your equivalent load. Okay, so the equivalent load equation is still the same, right? The equivalent load equation is still so this is our equivalent load. Right? So this is our By, and this is our moment at point B, right? Can anyone tell me what is the distance from here to here? Anyone? What is that distance? Huh?
2.
2. Why 2?
2 over 3 multiplied 6. No, 1
Yeah.
over.
Yeah, okay. So that distance you assume that is 1/3, yes or no?
Yeah.
It's wrong. It's not 1/3 because this is not a triangle.
Oh, yeah.
Yeah, this is not a triangle distributed load, right? So we don't know. Okay, so this is a trapezium. I don't know how to spell trapezium now. Okay, I'll find out. Okay, trapezium distributed load. Okay, so it is not, so x is not equal to what? L over 3. It's not equal to L over 3. Right? So now you have to divide your problem into two parts already. So we have to use, okay, use what we know. Okay, we have to use the superpositioning method. So what do I mean by the superposition method? So we know that our distributed load is like this, right? We know that. So we know this, right? So we know that this is 6,000. This is 18,000. So this will be equal to, you divide the load into 2. So the load will be, first you have a evenly distributed load. So this is 6,000, right? And then you add the other distributed load. Now you have to be careful. Now this is 0. Now this is 12,000, right? It's not 18,000 because you have used your what? You have used your 6,000 already. Yes or no? So that is what I mean by the superpositioning method. Okay, why we deliberately use that, so that we know when we do this, so that we know that this is evenly distributed. This is a gradient distributed, right? We use these two distribution because we know where the equivalent load is acting on, right? So from here, later on, we are going to do summation of the shear force, summation of the bending moment. So you have to add both of them. So this will be the shear force in evenly distributed load and the shear force of the greater distributed load, all will be as a function of x. Okay, so likewise, moment of the evenly distributed load in a function of x plus by the moment gradient distributed load as a function of x. Okay, so this is where the steps gets longer, but it's not necessarily more difficult, it's just more lengthy. Okay, so then from here, I'm going to divide this into 2 again. Hopefully I can finish the whole thing on the table. Okay, so on one side, we are going to deal with the evenly distributed load. So we know that this is an evenly distributed load, right? And then from here to here is a function of x, right? So this is what we know using positive shear, positive bending moment, and over here our equivalent load is omega x or 6,000 x. And then from here to here is your x over 2, right? So we start solving this using static analysis, summation of forces in the y direction. You guys are really good at this now. So this is equal to minus v as a function of x minus by 6,000 x. The whole thing is equal to 0. V as a function of x is equal to minus 6,000 x. Yeah, that is your minus 6,000 x. Okay. Then from here, we go into your your gradient distributed load. So your gradient distributed load, right? So what you have over here, so from here to here is your what? Is your x, yes or no? Is your x. Then the gradient distributed load, so this is v as a function of x. This is m as a function of x. So you have to find what is your equivalent load. Okay, so down here you require more working. Okay, so this it will be x as a function over 3. Okay, so how do we find the equivalent load? So I'm going to find a equivalent load equation. It's like what we find before. Before we do that, we need to find the equation of the distribution load. Okay, we have to find the equation of distributed load. So we know that now I'm going to draw x and omega. So this will start from 0 and n at what? 12,000, right? And this is 6, right? So omega as a function of x is equal to 12,000 x. Yes or no? Right? That is 12,000 x. Okay. Then we are going to integrate. Okay. So it's 12,000 divided by 6. Sorry. Okay. So this will be equal to 2,000 x. Okay. And then the equivalent load will be equal to 2,000. You integrate. Okay. So you integrate omega as a function of x dx. Okay. So this will be equal to 2,000 x squared divided by 2. So it's equal to 1,000 x squared. Okay. So, oh, sorry. I just you guys should tell me if I'm writing something. If you can't see it, tell me. Okay. Don't. Oops. It's coming back. Okay. Tell me. Don't just don't tell me. Okay. Because now you cannot see anything anymore. View page width. Okay. So the equivalent load now is equal to 1,000 x squared. Okay, so that's equivalent load. So from here, right, the equivalent load, we know that this is equal to what? So now we know that this is equal to 1,000 x squared. Right, we know that there's 1,000 x squared. So now we can start dealing with our summation about forces in the y direction. Okay, summation about forces in the y direction. So it will be equal to minus 1,000 x squared. So over here, I do apologize. Okay, so all this I should change them because this is I call this evenly distributed load as a function of x, moment distribution, moment evenly distributed. So what I'm finding down here is minus v e as a function of x. So this is v e as a function of x is equal to minus 6,000. Okay. So we are going to do static analysis. Okay, so likewise, I'm going to change over here. V gradient as a function of x, m gradient as a function of x. Okay. So from here, so we have minus v gradient as a function of x, and then minus by what? 1,000 x squared. The whole thing is equal to 0. So the shear force, right, is equal to minus 1,000 x squared. Okay. So from here, we know, okay, so from here, we know that the gradient or the shear force, so summation about shear force as a function of x will be equal to minus 1,000 x squared minus by 6,000 x. Okay, so we have seen this before, right? So if we were to go into the technique that we have used earlier, right? So the technique I used earlier, so we found that the equation is exactly the same. So v as a function of x is equal to 1,000. Well, I'm gonna highlight this. Okay, I'm gonna highlight this. So it's equal to, so this equation over here, right? This equation over here that I'm going to draw now, right? That I'm highlighting in yellow now. Yeah. Go on, my bad. So that equation that I'm highlighting in yellow now, okay, that I'm highlighting in yellow now, equation 2a, is exactly as the equation that we have derived. It's exactly the same. But the method we use is superpositioning. Okay, you can see that now. Okay, so I'm going to do quickly the moment. Okay, so I'm going to squeeze in if I can. Right, so we're going to take moment again.